In November 2022, ChatGPT made AI feel simple. You type something into a box, and a few seconds later, the model answered. And for many, this began the story of generative AI. Bigger models, better benchmarks, and smarter answers. But behind that simple chat box, a very different story was starting to unfold. Because serving a large language model is not like serving a normal API. Because a normal API request goes in once and comes back once. A large language model generates one token at a time. So one user request might actually mean hundreds or thousands of repeated passes through a model. And at every single step, the system has to remember what it's already processed. That memory is called the KV cache, short for key value cache, and it stores the attention keys and values the model's already computed, so each token doesn't require starting over from scratch. And in production, the KV cache became one of the biggest bottlenecks in the entire system. Not the model weights, not the entry point, the memory used to keep track of attention during generation. So in 2023, researchers out of UC Berkeley introduced vLLM and PagedAttention, a system that was inspired by virtual memory and operating systems. And instead of treating KV cache memory as one big, fragile block, vLLM broke it into pages and managed it more efficiently. The result was not a small optimization. The original vLLM paper reported 2 to 4 times higher throughput compared to the prior state-of-the-art systems at similar latency. And the project exploded. Today, vLLM has more than 81,000 GitHub stars, more than 17,000 forks, and almost 3,000 contributors. It supports hundreds of architectures and runs across NVIDIA GPUs, AMD GPUs, CPUs, TPUs, Apple Silicon, and more. It became one of the most important open source projects in LLM serving. But then the problem changed again, because once companies moved beyond demos, they were not just running one model on one machine, they were wanting to run multiple replicas across clusters, across clouds, with disaster recovery requirements, with long context agents making repeated calls, with users expecting that low latency, with GPUs that are expensive, scarce, and very easy to waste. Suddenly, the question was no longer just, how do we make one model serve fast? It became, how do we coordinate an entire inference system in production? So if an agent sends 10 requests in a row, do they land on the same replica? If one pod already has the KV cache, does the router know that? So if traffic spikes, do we prioritize the customer-facing workload or the batch job? If prefill and decode have different compute patterns, should they even run on the same node? That is the layer llm-d is solving. llm-d is a newer CNCF sandbox project that's founded by Red Hat, Google Cloud, IBM Research, CoreWeave, and NVIDIA. It sits above the model server and focuses on the orchestration layer. So intelligent routing, prefix cache-aware load balancing, KV cache management, flow control, and distributed inference on Kubernetes. So this episode is really about 2 shifts. First, how vLLM helped make LLM serving practical. And second, why serving inference with vLLM is not enough for real production use cases. So today I'm joined by Rob Shaw from Red Hat, who works closely on vLLM and llm-d and within the open source inference ecosystem. We talk about how inference evolved from a single runtime problem into a distributed systems problem, why routing and cache locality matter so much, enterprise AI deployments and their challenges, and why the next frontier of AI infrastructure may well be the coordination layer around the model. Because the future of AI is not just about smarter models. It's about whether we can actually run them in production efficiently. Welcome to Alexa's Input. Let's get into it.
When you're a team who's planning for production inference, you are very, very, very likely going to have more than one replica in your environment. Maybe when you're kicking the tires and just getting started and you have very low traffic, you'll have one replica that can process the request or 2 replicas that can process the request. But as you start to have tens of replicas, the service becomes more and more expensive to operate. A lot of the logic behind why we've invested in llm-d is to just provide operators with tools in their toolbox to try to get as much performance as possible out of their at-scale inference deployment.
Thank you, Rob, for joining me on the podcast.
Thanks for having me. Excited to be here.
I saw that you have a computer science degree from Harvard, but you actually went on to be an analyst. What's the story there?
Yeah, I didn't know you were going to expose me like this. But yeah, no, when I first graduated from college, I wanted to learn a little bit about the macroeconomic and overall business industry. So I joined the dark side for a while and invested in a lot of open source infrastructure companies and learned a lot about how capital markets work and things like that. And so it was a really fun experience at Bain Capital. I've applied a lot of the learnings about business models and things like that to my time at NeuroMagic and Red Hat.
So how did you originally get into working on AI infrastructure?
Yeah, so after I kind of finished up my time at Bain Capital, I knew I wanted to do something more entrepreneurial. Like I had been working in kind of like traditional mega cap PE, which gives you like a lot of different exposure to like lots of different companies, lots of different end markets. And I was really interested in focused on like infrastructure software. So we invested in a variety of different stage companies in the infrastructure space. So I knew I wanted to work in the infrastructure space. I actually joined NeuroMagic because I wanted to work for like a Series A stage company that, didn't quite have product market fit yet and was trying to sort of figure it out and learn about how to, kind of operate an early stage business. And so I got connected to Brian Stevens, who is the CEO of NeuroMagic. I, really wanted to work with Brian, which was a good instinct for myself back in those days. So I really joined the company to basically work with Brian and learn the ropes of how to, kind of operate an early stage infrastructure company. Then maybe like 6 months later, ChatGPT launched and AI became a very, very hot field. And there was a lot of investment over the course of the past few years. So I got a little bit lucky. I didn't go into it with the thesis that GPT-3 was going to change the world, but right place, right time, I guess.
And it's funny what you say about wanting to work with Brian. Everywhere I've worked, it's the people more than anything else that makes me want to work there.
Absolutely. Yeah, he's a great leader and, has a lot of experience through the early days of RHEL, through Google Cloud. And so, I knew like working with him, we would try to figure out a business model around AI. And, that's really what I've spent the last 4 years on is figuring out how to combine community strategy with business strategy, with partner strategy to, really build a business around infrastructure software.
So what specific problems were you excited about solving there? You also started there as a product manager, right?
Yeah. So at the time when I joined NeuroMagic, we were actually working on CPU inference LLMs were out, but they weren't really mainstream at the time. This was kind of like before ChatGPT launched. And so we actually were working on building inference runtime for CPU and for traditional deep learning models like BERTs and YOLOs for object detection. So I knew we were working on production. So like inference is the production problem. It's we're actually going to put this behind a real working system that's solving some business use case. So I really like working on production systems because that's where there's a lot of cost. That's where there's really high importance in reliability, and that's where there's a lot of kind of like operational concerns about like, how do you kind of keep this system up and running? We were originally kind of like working on the problem of inference for CPUs. We had a proprietary inference engine called DeepSparse, and we had developed all sorts of, kind of like compression technologies to try to make the CPU models work as fast as possible try to make these deep learning models run as fast as possible on CPUs. And, honestly, like we didn't have a ton of traction doing that. Like the models, first of all, like the GPUs were pretty good. The second thing was running deep learning inference for BERTs and YOLOs was a big thing that large tech was doing. But, enterprise and really anyone outside of anyone running ads just didn't really have this as one of the core problems. And so when LLMs, came out in the end of 2022 and then into 2023, everyone's eyes just opened up about the power of deep learning, and the LLM inference market became very important and one of the probably like largest software markets in the world. And so that was a huge, wind at our back that sort of changed. And then the other thing is we kind of decided to leave behind the CPU world because we realized that we could apply the same ideas, the same team, the same technologies that we were applying to CPU, that we could do that on GPUs, which is what's really going to be needed to run some of these very, very large models. And so we pivoted the company in 2023, towards the end of 2023, to work on LLMs and do it in the context of vLLM, which was an open source GPU-based LLM inference engine. But with really like the same idea of like bring all these high performance computing engineers, bring deep model optimization experience, and try to build an enterprise inference stack that made all the LLMs run really efficiently.
You were in on the vLLM project pretty early, right? You're a maintainer of it as well.
Yeah. So like the main thing that we basically did is vLLM, came out in the middle of 2023. The folks at UC Berkeley, Simon, Wusuk, Johan had started the project, and it really emerged as an open project from Berkeley. So there was a couple things that were very attractive. It was Apache 2. It was deliberately sort of set up to be a multi-organization contribution project, and it had really good performance and lots of model support, and it ran on multiple accelerators. So this was very attractive, and we evaluated getting involved with a couple different communities, and this one was just really off the charts in terms of the community that was developing around the project. And so our overall strategy at Neural Magic was, and continues at Red Hat, was to be a leader in the vLLM community, have a good percentage of the maintainer group, and then build enterprise distributions of the open source inference stack around that. So yeah, I got involved with vLLM towards the end of 2023. And then our whole team, as we kind of left behind our CPU-based strategy, got involved with vLLM. And to this day, Neural Magic and Red Hat have been some of the biggest contributors to vLLM and work on all the major subsystems across the project.
What did you take from Neural Magic? What was the big lesson that you learned that you took with you to Red Hat?
I'm trying to learn more and more every day. I mean, I think one of the major things is like the AI space is moving very, very fast. And so it's really easy to have a thesis and be dogmatic about like what you think you should be doing. And we've made plenty of mistakes along the way of trying to start certain things and then that doesn't work out, or trying to start some business and that doesn't work out. But I think the main piece is to be flexible with like what we're doing and continuously listen to customers, listen to what they're looking for, evaluate the market, and try to adapt your product strategy as quickly as possible to the domains, and continue to invest ahead of where customers are and making those speculative bets and not being afraid to be wrong. That was a major thing, switching the company in terms of our strategy from sparsity on CPUs to working on an open source GPU-based inference project. We had very similar skill sets in both of those, but it was a much, much different business strategy that we took. And so I think that's been one of the things I've tried to keep going at Red Hat, is like continuously understanding what our customers are asking for. And, if we do something that I like and it ends up not working out, being okay with shutting that down and moving on to the next thing that the customer is asking for. So I think that's one of the key things, is to always have this iterative product development, listening to feedback and continuing to evolve based on that. And then the other thing is like the power of the community projects. So, it's really, really hard in AI to build your own product and have a proprietary thing that only you contribute to. There's so much innovation. And so, especially with llm-d that we'll talk about later, I think getting involved with these community, vendor neutral, lots and lots of contributors making the project better is like a very good tailwind to have.
Speaking of that, Red Hat focuses on building open source. What made Red Hat a place that you wanted to stay after Neural Magic was acquired by Red Hat?
Yeah. So, I mean, I have had this mission to, build this open inference stack for the past couple of years, which is all the model, all the accelerator, all the different layers of the stack. And so joining Red Hat, it was just like a perfect fit, where the strategy that we had at Neural Magic to work in these open source communities and then build enterprise products around that, we just got to continue doing that at Red Hat. But I think the thing that's been a huge accelerant is Red Hat has a lot more resources. So we just have much more access to work more closely with customers to get us feedback more quickly and make sure that we're on the right track as it relates to our product roadmap. So that's one, is the customer and feedback is just very helpful for deciding where to invest. Then the other piece is Red Hat has lots of experience in the Kubernetes and orchestration layer. There's a lot of deep expertise in the Kubernetes networking stack, in the deployment automation, CRD stack, obviously with building enterprise products around simple things like install, lifecycle, CVE remediation. All of these, I wouldn't call them boring, but they're critical pieces of critical requirements to work with enterprise customers that are, there's a lot of embedded knowledge inside of Red Hat for how to do those things. And so we've been able to dramatically expand the pace at which we've been able to build a product that is satisfying all the needs of enterprise customers for their inference stack. And I think it would have been very hard to do this at Neural Magic standalone. And we had even tried to build some of the things that we've been able to build at Red Hat, and we just didn't have enough resources to be able to go after it. So it's those two things. It's kind of like continuation of the mission that we had at Neural Magic. And then in addition, accelerating all the product initiatives that we had with just all the embedded expertise that Red Hat has in the Kubernetes layer and in the enterprise hardening processes that we have for how we build and ship our software.
And how would you explain your role at Red Hat now? What are your responsibilities and what do you do?
Yeah, I mean, when I first started at Red Hat, I was an engineering director. So the overall team from Neural Magic all reported to me. We did the integration into Red Hat. Tanim, who now is the engineering director, came on from the Red Hat side and helped to integrate, and we worked together to manage the team. And then over time, Tanim took on the director role, and I switched back to an individual contributor role. So I have a made-up title called member of the technical staff. Basically, my job is to do two things. One is to make sure that the open source projects that we work with are successful. So vLLM, llm-d are the two that I primarily focused on making sure those projects are winning and are doing well for the long term. So this is roadmap, facilitating contributions from third parties, marketing the projects, so on and so forth, evangelizing the projects, so on and so forth. So that's one of my focuses. And the other is on making sure our customers are successful using those stacks. So this is working in pre-sales processes to help the customers to evaluate the software. This is working with customers who are already onboarded and making sure that they're successful with their deployments, with enablement. So I work a lot with our field teams, our forward deploy engineering teams, our services teams, who are all working with customers to make them successful. I am involved with as many of the major accounts as I possibly can to try to make their deployments successful, because the Red Hat product is more than just software. It's all the expertise that we have in engineering and in our field teams. And so, yeah, I try to make those as successful as I can. But those are my two OKRs for 2026, is to make our customers successful with the open source projects and then make the open source projects themselves successful.
Small OKR there.
Unfortunately, I don't actually do anything anymore. All I do is, make roadmap slides.
But I beg to differ. You're everywhere, but like in a good way. I think you're very helpful to customers. Let's go into vLLM and llm-d. Can you talk a bit about what problems they solve? Maybe you can start with vLLM.
Yeah, sure. So vLLM is like what's called an inference runtime. And what the runtime's job basically is to do is to be the Rosetta Stone that maps the models onto the accelerators. And so if you think about it, a model, what is a model? A model is an abstract function which, given a set of tokens, predicts the probability of the next word in the sequence. And this model is like a configuration file and a binary blob of weights. And so vLLM is the thing that takes that binary blob and that configuration file, which specifies what the function is, and maps that model onto the accelerator. So there's two main things that an inference engine has to do. The first is to batch requests. An inference engine is going to be responsible for dealing with multiple concurrent requests that are trying to consume resources from the system. And so vLLM's first core job is to do something called continuous batching, which is the process by which work is scheduled. So when you're processing an inference request for a particular query, maybe the prompt is the quick brown. The way that this generates tokens is by basically auto-regressively calling the model over and over again. So you say the quick brown predicts the probability of the next word. Let's say that's fox. Then we take the quick brown fox, pass that off to the model again, and it generates jumped, and so on and so forth. And so continuous batching is basically the process by which the vLLM scheduler interleaves multiple different requests that are all trying to do that same autoregressive process at the same time. So that's kind of like the core fundamental thing. vLLM is like a work scheduler that's doing very fine-grained resource sharing between the different requests that are all trying to make progress at the same time. And the second key thing is there's something called KV cache. Basically, when the models are generating text, they have something called attention, which is the key kind of operation in a transformer. And it turns out that in that autoregressive process where you're calling the model over and over again, we can reuse one of the intermediate states to avoid reprocessing the prompt over and over and over again. And these intermediate states are called the keys and values in the attention operation. And so the other thing that vLLM is doing is managing this KV cache memory, because it can be, on the order of gigabytes per request. So it's a very, very precious resource that has to be maintained or has to be managed properly. That's kind of what vLLM is doing, is it's this continuous batching engine, and it's this KV cache manager. And then there's a million different optimizations that you can do to make that as efficient as possible. Offload the KV caches, send them around between nodes, all this different stuff. But fundamentally, those are the two things that vLLM is doing. It's, sharing the GPU between multiple requests through continuous batching, and it's managing that KV cache memory. And everything else is just an optimization on top of those two, fundamental concepts. And so vLLM is the place that lets you take all these different models, Llama, GPT OSS, Qwen, DeepSeek, whatever, and be that single runtime that does this KV cache and continuous batching that runs the models across a bunch of different hardware accelerators, all the different NVIDIA SKUs, AMD, Google TPU. So it's that Rosetta Stone's runtime software that maps all the different models onto all the different accelerators and does all the key performance optimizations that are needed to make that as efficient as possible.
And so predictive inference had quite a few of these, like you said, BERT or sklearn that you could use out of the box. But with LLMs, there were different problems to solve. So they needed a new model serving runtime, if you will.
Exactly. I think the fundamental difference is for predictive models, you would get an input and then you would pass the input to the model one time and get a result back. And this is a very simple kind of process by which the model generates. So typically there was something called dynamic batching, where you let requests queue up in the server and then dispatch them all off to the model at the same time, batch those together, but it's still fundamentally one forward pass per request. With LLMs, we have a much, much different dynamic, because each individual inference request, if you generate 1,000 tokens, that actually requires 1,000 forward passes through the model. So all of this continuous batching, KV caching, etc., is fundamentally to deal with the fact that each inference request is actually a series of calls to the models in this auto-regressive fashion. And this is what creates all the complexity as well as all the opportunity to optimize. And the other thing is LLMs are gigantic. They're L for a big reason. These models are huge. They're very compute intensive. Performance is at an absolute priority for anyone running an LLM system. The reason that vLLM becomes complicated and the reason why you implement all these different performance optimizations is because the bang for the buck on implementing those optimizations is very, very large, because we're talking about serving 100 billion trillion parameter model on, GPUs that cost $2 an hour per GPU, and maybe you need 16 of them. So the cost can really add up. You have a more complicated model to serve and more complicated inference process to deal with. And then at the same time, it's really expensive. This means you want to do every possible optimization that you can.
And I want to get more into the details of this, but first, maybe let's just talk about why did vLLM alone stop being enough? Why was llm-d, a separate project, needed?
I wish we could have called the project vLLM-d, but the key idea with llm-d is that it's a distributed inference engine. So what started to basically happen is vLLM got really, really good at processing an individual request on a single node. But a major trend started to occur, which is we started wanting to optimize at the router level as well. So if you think about it, most of the time, what most people do when they want to scale out any sort of microservice, but LLM could be an example of this, is on Kubernetes, you create a deployment with n replicas, and you put a service in front of that deployment, and this allows you to round robin requests to each of the backends, and then you can scale the system. That's a very, very common pattern. However, in the context of LLMs, this can fall apart for a couple of key reasons. One is, and most importantly, LLM request patterns are multi-turn. And this has become especially important for agentic applications. Or if you think about Claude Code or whatever agent that you're running, what happens is the model runs in this kind of inner loop, and it plans, and then executes a tool, looks at the result of the tool, reasons, plans, so on and so forth. Each one of those tool calls creates a new request to the model. So one user session can result in n requests to the model. As like a canonical example of why you need LLM aware load balancing, if you randomly round robin those requests to one of 100 pods that you have running, you're going to have to recompute that KV cache state for the same prompt over and over and over and over and over again. And you're going to spend, and for agentic applications, the average prompt length is 80,000, and the prefix cache rates that you could get in theory are 90+%. So you're just going to be spending all of your time recomputing the same prompt over and over and over again. So something like prefix cache aware routing, where the load balancer is aware that, hey, pod B is going to give me a cache hit. Okay, like I absolutely need to route that request to pod B. So this is an example. We can add this kind of LLM awareness into the load balancer level, implement things like KV cache aware routing, and really improve performance. Additionally, there's been other trends in open source LLM serving. So another example of this is called prefill decode disaggregation, where prefill is the prompt processing phase, which is the place when we take a prompt and process the prompt and kind of pre-fill the KV cache state. And then decode is the auto-regressive phase where we're going to generate one token at a time. These have very, very different compute dynamics, and the pre-fill phase can actually interrupt the decode phase. So there's an opportunity to split pre-fill and decode into multiple nodes, which can then allow us to kind of independently optimize the pre-fill and decode phase. This is called PD disaggregation, and it requires an orchestrator to deal with the protocol associated with all those things. So this is another example of how a naive service doesn't quite work, and vLLM needs a distributed orchestrator to orchestrate a PD inference request. Another example is something called wide expert parallelism. These mixture of experts models typically can be deployed over multiple nodes for these very, very large DeepSeek models. And especially when you think about the modern NVIDIA systems like the NVL72, which have these there's 4 GPUs per node, but then you have 72 total GPUs connected via NVLink. You're going to want to deploy those over multiple nodes. And so a wide expert parallel system where we're actually going to deploy multiple pods. Those pods are kind of part of a single logical unit for serving the model. These things start to become very important when we're dealing with very large models on the newest hardware. So these are kind of the key ideas that llm-d has, is LLM aware load balancing, and then building orchestration for a lot of the distributed inferencing features that have started to become mainstream in vLLM. And there's other stuff that's going on in the project, like flow control for multi-tenancy or batch inference, or integrations with RL frameworks, or KV cache management through the storage and memory hierarchy. So this is a very, very rich project with lots of distributed performance optimizations, but those ideas I just kind of talked about of smarter LLM load balancing and then disaggregated serving are the key reasons why we created the project. Since in vLLM, we were starting to make these primitives available, and then llm-d is the way that we actually use them in a production system.
So vLLM is managing within a single instance. llm-d is managing multiple vLLMs running, so distributed more than one replica of a vLLM running or a model running. And this is important probably for most people in enterprise or pushing to production, especially if you're managing your own models, either in some EKS or on-prem. Because at Bloomberg, for example, we need to be what we call DR-1 compliant. So disaster recovery -1, which means we need at least 2 replicas of every service running, usually actually on 2 different clusters. That's what's pushing this operational complexity of owning a distributed system, but it's making it worth it because you need all these intelligent routing layers to make that more cost efficient.
A key way to think about it is it's a combination of no one who's running at any amount of scale is ever going to have one replica of vLLM. These LLM services can handle 32 concurrent requests. As you start operating with more scale, you suddenly have multiple replicas that you're going to be dealing with, and there's lots of distributed performance optimizations to do that can take full advantage of the cluster resources. And so that's what llm-d is solving fundamentally, is how do we build cluster level optimizations that allow us to do better than a deployment in a service. Now there's separate concern, which is how do I have consistent deployment automation? How do I set up my monitoring? How do I set up my failover? All of these things. And projects like Kserve, which is what we use, and I know you guys used at Bloomberg and started at Bloomberg, is very, very useful for providing that consistent, simple CRD that the platform teams can use to automate the deployment of llm-d. So that's kind of like how I sort of view it, is like llm-d is like the deployment architecture. It's like the runtime, the distributed runtime that's implementing all the key performance optimizations. And then Kserve is the way that we consistently deploy that, in highly available mode to automate the deployment process and make it easy for the platform teams to have consistent operations when they're running the models.
Yeah, completely true. Kserve made it super easy to give our AI teams a way to consistently run their models at scale. So yeah, that's the great thing about Kserve, and it works really nicely with vLLM. Would you say then that anyone running more than one replica of their model should use llm-d?
I think that in most cases, the answer is yes. Even for a very simple deployment where you're looking at something like prefix cache-aware routing, like this is just like a very, very simple optimization to apply. And so I think in almost all cases, like as soon as you have more than one replica, some of the features of llm-d can start becoming very, 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 very useful right out of the box. I will say there is some more Kubernetes networking that, gets, I wouldn't say in the way, but adds some more complexity over a simple service. So, I think if someone's just kicking the tires for whatever reason, there's utility to using very, very simple primitives to deploy. Almost most use cases, something like llm-d is a pretty simple way to really add in that basic LLM-aware load balancing for pretty low amount of complexity. Something like prefill decode disaggregation or wide expert parallelism is not something that should be used in every single deployment. But those are actually like pretty complicated optimizations that you're going to want to use for your most scale workloads, but probably not for your average workload. And one of the things we've done in llm-d is organized around these well-lit paths, which are different deployment architectures. Something like the optimized baseline that we have, which sets up prefix and load-aware routing, is very, very simple and can really lead to pretty significant performance wins for a relatively low amount of additional complexity.
Yeah, so like route based on how much capacity is being used in a certain replica or where we've seen this prefix before. Like those are the two simplest ones you'd say that people should definitely start out with.
Absolutely. And then there's other techniques like, if you're doing batch inference, for instance, we have a whole series of modules for offline batch, which is like much different from the online serving setups. One of the things to kind of be aware of is like there's kind of like different deployment architectures, and not every deployment architecture is going to be useful for every deployment. But I think that almost all deployments can benefit from at least one of the features that we have integrated.
So can you talk to me about what common challenges emerge when inference becomes distributed?
When you're a team who's planning for production inference, you're very, very, very likely going to have more than one replica in your environment. Maybe when you're kicking the tires and just getting started and you have very low traffic, you'll have one replica that can process the request or two replicas that can process the request. And when you have a smaller amount of scale, this is important. You want to have a reliable service that can operate. But as you start to have tens of replicas, the service becomes more and more expensive to operate. And so a lot of the logic behind like why we've invested in llm-d is to just provide operators with tools in their toolbox to try to get as much performance as possible out of their at scale, inference deployment.
Yeah, I would say maybe one problem would be understanding based on their use case, the best configurations probably.
Yeah, I think that makes sense. But one of the things we've tried to do is layer the optimizations. Everyone should get started with the optimized baseline. And then everything that they're layering on top of that is a potential new technique that can potentially provide value over each one. So this is one of the reasons we've sort of like structured the project around these like guides and well-lit paths, is to just provide some guided flows that allow you to layer more and more potential complexity into your environment over time.
So what do you see when people need to start deploying to production and they need to span things like region, provider, clusters? Maybe they have heterogeneous GPUs, or maybe they have various latency and cost requirements. What do you see in these setups?
A very, very common one that I see is folks focused on high availability and like disaster recovery. So a very common setup is that folks want to run the same model in multiple data centers and have a single URL that they can call into. In the Red Hat products, we've talked so far about the vLLM layer, which is the runtime, the llm-d and kserve layer, which is the per cluster deployment automation and optimization within each cluster. And then in front of that is something we call model as a service, which is basically the API gateway, where you're going to do things like authentication, token tracking, who has access to what model, how much rate should that, like rate limiting, things like that. And so a very common pattern that we've started to see is, folks deploying single kind of MAS layer and then multiple inference clusters behind it, and basically doing routing between those two data centers. This has been popping up in almost every customer that I talk to these days, where they want to have this centralized access and controlling, but then have multiple redundant data centers for, doing the actual inference workload. So everything that we've talked about with llm-d and kserve is like deployment automation within an individual cluster. But typically there's like another layer that sits in front of that, which is that gateway that then is farming traffic off to the different clusters that are going to have the actual inference running. So llm-d doesn't do anything for balancing load between cluster A and cluster B. Like llm-d is a cluster scoped project, which is within my GPU cluster. How do I get as much performance as possible? But typically someone will have something in front of that, which basically does which cluster should process this request and does that kind of centralized token tracking off, etc. That doesn't need to run on a GPU at all, and even could route to third-party models in the cloud, whether it's Bedrock or Claude or whatever that's up there. So this is a pretty common layered pattern that I've started to see, which is llm-d and kserve for per cluster performance optimization and deployment automation, and then the API gateway sitting in front as a orchestrator across multiple clusters for disaster recovery. And then also GPUs are scarce. And so sometimes customers have them in one cloud and another cloud and on-prem. And how do they balance between all of those? I've definitely seen folks with GPUs in multiple environments and looking for a way to deal with traffic across those different clusters that they have.
Yeah, I was going to actually ask you next, like what problems are customers most focused on right now? But I think you just answered that. And for those listening, Rob and I work together now. From the conversations that we've been in, I've been kind of not surprised, I'd say, but it's just been interesting how seems like it is the top of mind for everyone. It's this global gateway that routes to various clusters or providers or on-prem to make the most use of the resources that an enterprise will have.
Absolutely. And I think like this will become a very common pattern where, folks are going to have some models that are self-hosted, some models in the cloud. They're going to want to have redundancies of these across cloud. Maybe they're consuming first party and third party. They have self-hosted in one environment and another environment, and they really need that centralized access control, token tracking, who has access to what. But the other thing that I think is really useful once you have this kind of centralized gateway is you can start layering in more and more enterprise functionality around it. So one very common thing that I've heard a lot of people asking me about is like semantic routing. So, you hit this unified endpoint and you have some sort of router that says, okay, this query is hard or this query is easy. If the query is above some difficulty threshold, then send it to the most expensive, most complicated model. If it's a really simple query, send it to a lower cost model, for instance. So this like semantic routing thing. And then like a unified endpoint can do things like guardrails, where maybe you want to make sure that this model is producing non-profane content, or if I'm a customer service chatbot for XYZ bank, I'm not responding with Python scripts. That gets around. So anyways, this kind of centralized gateway, like in addition to allowing you to kind of secure, authenticate, keep track of which user is using what resource and who has access to what resource. There's also opportunities to layer on these other hooks of things like semantic routing to cloud or on-prem, or things like guardrails that, our enterprise controls. And then I'm sure there's other stuff that we haven't even thought of yet and our customers haven't even thought of yet that will be layered in the future. So I really like this idea of like the unified gateway and then multi-cluster inference as a way to create high availability, disaster recovery type situations where you're robust against an entire data center going down, while also having it be able to implement all of these interesting features, gateway or guardrails or semantic routing. And, at the end of the day, there's just a database that's needed to be replicated to keep all those things in place. And so I'm sure we'll be able to make the gateway itself be multi-cluster to avoid that as well. So anyways, I really feel like distributed inference, like the pieces we've talked about with vLLM and llm-d, it's, vLLM is pretty mature. It's a 3 or 4 year old project at this point. The ecosystem has really consolidated around things like vLLM and SGLang. And so it's pretty clear what those projects are at this point. llm-d is still evolving very quickly, but I also think it's getting more clear about like, okay, this distributed inferencing layer is what it is. These optimizations are useful, and now customers are going to adopt them. This AI gateway is definitely the most in flux in terms of where the action is, where a lot of the ecosystem is going to shake out, over the course of the next 6 to 12 months. And so this is where we're putting a lot of investment for our 3.5 release of Red Hat AI, and we'll continue to push through the rest of this year and into next year in terms of rapidly evolving that layer of the stack. And then we'll be working closely with our customers. One of the challenges with this multi-cluster stuff is like customers will have different environments, different configurations. So, we'll work very closely with our closest partners to design and deploy optimizations that fit within the systems that they have. So I'm very excited about next 6 to 12 months, like as it relates to this AI gateway, because I just think it's going to be something that comes up over and over again.
Yeah, definitely. I think just from my experience, because I had built Signal via Gateway, it's just so interesting to hear this come up often. It's a bit validating because I have so much context on it and I'm so interested in it. But like, for example, even if you're someone like Bloomberg and you traditionally have run everything on-prem because you want to use so many GPU resources, like you are most likely multi-cloud. I think that it changed through time which cloud we were more invested in, regardless. So I think that this architecture definitely makes sense. And I would say even that if you have more than one cluster, if you don't have this global gateway that's routing, you won't even be able to use maybe some of the advantages that things like llm-d give you. If you're not routing to the cluster that has the KV cache that you've already used, then really what is the big advantage of having it if you're not routing to the right cluster? For example, we were running a model in 2 different, let's say, GCP clusters, but we realized we were never using the cache because we didn't have sticky sessions and we weren't actually routing to the correct cluster. If you don't even have the routing down, then you won't be able to use the advantages of llm-d, for example.
Absolutely. And this is one of the challenges is like there's so many layers of optimization, and making all those things work together is non-trivial. And so I think this is actually one of the best parts about working at Red Hat, and like coming all the way back to like where we started. When we were at Neural Magic, we were just working in the vLLM runtime, and there's clearly so much more to the story here than the inference engine. The inference engine is critical. Like it's the dial tone centerpiece that powers inference, but we need to make all these different layers work together very, very well. And so this has been super successful in llm-d, where we like brought together the Kubernetes networking ecosystem with vLLM ecosystem and really rapidly co-developed this layer. And then I think the next thing on top of that is this multi-cluster gateway layer, AI gateway layer. I hate saying the term gateway because it's such an overloaded term for a variety of reasons. But, with this next layer, making all those things work together is like super, super, super non-trivial. And to give an example of something silly, take something like the responses API. Most of the ecosystem has been built on top of OpenAI's V1 chat completions API, which is like a simple stateless API. So all the different layers plumb things up and down. When we started thinking about responses API, or messages API, which are like kind of the next gen versions of these that are built more for agentic applications, where you have a tool calling loop where the model, it's going to require multiple inference requests per user request. These get more complicated, and we really need to make sure that the vLLM layer and the responses layer and the tool call layer all work together properly, because very, very, very small issues at any layer of the stack can create like catastrophic end-to-end performance, end-to-end quality results. So anyways, this is a big part of like why I think we're well positioned at Red Hat to help customers with all these different layers is like we just have expertise at every single layer. Joe, who runs the AI BU, says from metal to agent, but like it really is true. It's operating system, Kubernetes layer, vLLM layer, llm-d layer, kserve layer, MAS layer, gateway layer, all these different things. Like Red Hat is leading this whole ecosystem. And so we can really support customers to make sure that the stack really works together and, provides a really great experience for, running your LLM serving stack.
I've really enjoyed falling into the center of this whole evolution because when I went to work at Bloomberg, I was working on Kserve, but to be fair, it was quite a mature product then. And I was working on, I think every platform team, the goal is to abstract away the underlying platform. For example, I was building the backend API when we were just doing predictive inference. And what we we're trying to do is from the UI perspective, just make it clear what the person should do if they had something wrong with their service to fix it. What we were doing before, we were just surfacing those status low-level errors from a Kubernetes resource. So I think that was a pretty mature stage. And I feel like when Gen AI became a thing and we would need to build a platform around that, we kind of started way lower on the stack of abstraction again. And now we're trying to make it easier to run. So I think that coming from where predictive was quite mature to Gen AI, same space, but quite immature, this evolution that's been pretty quick over the past couple of years has been fascinating.
I totally agree. And I think it's because there's so much. One of the things that's interesting about like Gen AI serving is like, it's just such a bigger, more important category in some ways. It's like predictive AI was like big and was important, but like Gen AI serving it's a board level, initiative for every single company in the world. And so there's just so much demand and things are moving so fast. And people got to do hybrid stuff of on-prem, in the cloud. They got to deal with agents. They got to deal with, all this new stuff that's happening very, very, very quickly. And so I think it just creates a lot of like fun engineering problems. And I'm hoping that we can pull together all the pieces that folks need to get up and running so that they can focus on the business problems and not on the technology problems. So anyways, that's why it's definitely been a fun couple of years working in this space.
Yeah, and to your point, there are a lot of different type of optimizations and advancements coming into play, from different types of processors to small language models being an option. Why do you believe that llm-d represents the future direction of inference infrastructure?
I just believe in this overall open source inference stack. Like, I just don't think that this type of something so fundamental, tends to have open source software that drives the ecosystem because too many people are involved. It moves too fast. The performance is too important. Like, it just tends to be commodity software that wins this layer in a broad state. And then I just think that the performance optimizations we have in llm-d are just very broadly useful. And what that means is everyone will want to adopt these optimizations in the same way that everyone has wanted to adopt vLLM as opposed to like just doing something naive with, transformers. Like, I remember like when LLMs first came out, like Kserve put like a Hugging Face pipeline of an LLM and did dynamic batching around it. It's so obvious that everyone would have shifted to vLLM, something like vLLM eventually. And so I just feel it's very inevitable that this LLM distributed optimization layer is going to become something that's very prevalent and is just obviously used in almost every deployment. And why is llm-d going to be the thing that wins that? I mean, I'm sure there will be other projects too, just like there's competition for vLLM, but llm-d is vendor neutral. So, it works across NVIDIA and AMD and, Intel and Google TPU. And then it's a CNCF project. So we have really broad contributor base from obviously Red Hat and Google and IBM Research, who have kind of led the project. CoreWeave is involved. and recently we've been seeing folks from Microsoft and Amazon and some of our partners in RL. So I think at this point, like we have enough of that kind of like community momentum that helps the project to just really push along, because it will just become something that is an industry standard. So that's kind of like my overall goal, is by establishing it in the CNCF and welcoming in all these different contribution bodies, that we can really work together to make the project be something that is useful for as many deployments.
So what changes if something like small models become extremely popular? And let's say they become just as good as the large ones are now.
I mean, I think you will always see that the frontier models have an advantage over small models, but what tends to happen is all of the models are getting better. So smaller models can be useful for economically viable tasks. And so I think what you will continue to see is like hybrid approaches, where companies have small models that they serve, medium-sized models that they serve, large models that they serve, and then have access to frontier models served by OpenAI or Anthropic, et cetera. So I think that you will continue to see customers having a mix of these, and gateway layers being very important for enabling customers to toggle between different models for different use cases. I don't envision like things will change significantly from what they are today, where like customers use a mix of models for different use cases, and small models will likely play a key role, especially for large scale but still economically viable tasks. As all the models get better, the percentage of tasks that can be solved with smaller models will likely increase.
Yeah, I totally agree. And I think that we'll start to see better understanding about when to use them as well. So let's get a bit more technical now, a little bit more of deep diving into some of the features. And let's just start with GPUs. Someone deploying an LLM often needs to understand, kind of surprisingly, a low level of infrastructure details around GPUs and the way they communicate. Why is that?
I somewhat agree with that, but I also like somewhat disagree, which is like, I think that it's generally useful to have some mental model of like what something like vLLM is doing. Like if you're an operator of vLLM and you see, okay, my KV cache utilization is at 100%, or you see that like, oh, the end-to-end latency is spiking, and you're trying to understand why that's happening. One of the reasons might be, oh, I'm out of KV cache memory. And so having some understanding of what's going on inside of the vLLM server is generally useful as a cluster operator. And the other piece is, there's knobs that can be used to tune performance, whether it's setting up the parallelism scheme or, enabling things like offloading, etc. And having some understanding of how the LLM works internally to the runtime can be useful for selecting what optimization might be useful for your work. But with vLLM, the user shouldn't have to understand what a CUDA kernel is and the details of how the tensor parallelism sharding works and things like that. But there definitely is some utility in having some understanding of what's going on in vLLM so that you can interpret the metrics that are coming out, make good operational scaling decisions, select which optimization to use when. I think we could do a much better job in Red Hat and in vLLM and make it, there's so many knobs that are available, and like, honestly, most of them should never be touched. We could probably do a better job of like clarifying like what are the key things they should be considering. And this is one of the things I always try to do when I go and meet with customers, is help them to build the intuition about what's going on inside of the server so that they can then be better operators, be better SREs of running the actual service.
What are some of the challenges around networking with GPUs, maybe when it concerns like Rocky, InfiniBand, RDMA? Why are these some of the challenging components?
Yeah. So, I mean, the key thing is like for many, many deployments of vLLM, you don't have to think about multi-node. Just to give a flavor. So each GPU node, has typically either PCIe, but more likely NVLink. If you're running on an H100 like SXM system, they have NVLink between the nodes, and vLLM internally deals with the NVLink stuff. So if you put like a pod down and give that pod access to 8 GPUs, vLLM just handles the NVLink networking internally and does the tensor parallelism collective operations that are needed to execute a forward pass of the model. So for single node deployments and aggregated deployments, InfiniBand and Rocky, which are like multi-node connectivity, which is going to connect one node to another node, that will allow you to interconnect basically more than 8 GPUs together. You don't have to think about it at all. Where Rocky and InfiniBand come into the picture is when you're starting to look at multi-node deployments. So this is to say, okay, if you have H200s, these have 8 GPUs per node, but you want to do prefill decode disaggregation, where you're going to put the prefill worker on node 1 and the decode worker on node 2. Now, all of a sudden, you need to connect those two nodes together. And this is where something like Rocky and InfiniBand is really, really useful, because we have to move a lot of data at very low latency between the nodes to do something like prefill decode disaggregation. Similarly, for a multi-node deployment of vLLM, where we're doing wide expert parallelism and sharding the model over multiple nodes, this is something that needs to basically happen. We need to have this multi-node networking. So I think the Rocky and InfiniBand networking is a little bit finicky. There's multiple different ways to set it up. There's not really yet standardization in the Kubernetes ecosystem for how this stuff gets exposed up to pods. And in general, it's just kind of complicated. And we're combining like much more complicated deployment patterns with more things that can go wrong, with less standardized infrastructure from the Rocky and InfiniBand side, which adds a lot of complexity to getting these systems up and running and being really, really performant. So there's a couple of things going on. One is in the Kubernetes ecosystem, we're trying to make this more easy to work with. So for instance, there's the DRA project, which is doing a lot of things, but one of the things that there is something called DRA-net, which provides a more standardized way for these networking topologies to be requested and provided to the different nodes, which will really, really help to standardize how networking gets exposed up to Kubernetes pods.
And that's dynamic resource allocation, right? DRA?
Yes.
Yeah.
Yes. And, other projects like DRA SRIOV, which is the successor to SRIOV, these things, which I'm not an expert in, so don't ask me any more questions about it. But these things are like solving the problem of like, how do we have a more standardized way for people building Kubernetes clusters to expose the NICs and networks up to the pods? And this is generally useful. I don't understand at all any of the technical details of how that works, but I am like generally aware that DRA, DRA-net, DRA SRIOV are basically generally solving this problem of the lack of standardization for how to expose the resources, the NIC resources up to the pods. So that's one thing. And basically today, there's a huge amount of heterogeneity in how that happens. You have virtualized setups, non-virtualized setups, different types of NICs, Rocky, InfiniBand. Every single cloud does it in a slightly different way. It's super, super complicated, and you basically have to go cloud by cloud and solve the problem. And so these primitives in Kubernetes will make this more standardized and allow folks like us that are building on top of Kubernetes to have a much better user experience in how we do things. And then from the vLLM side, a lot of these distributed performance optimizations have been new within the last year. So things like PD disaggregation with Nixel, this has been like a bleeding edge feature, which has now gotten a lot more standardized. So it's a lot more mature these days. It works a lot better. It's a lot more stable. There's a lot more error handling. There's a lot more telemetry. It's just now it's a production feature, whereas 6 months to 12 months ago, it was a bleeding edge feature. And then for YDP, which is like the multi-node serving, this has been a bleeding edge feature, and now it's becoming much more stable and mature. So I think on both like the vLLM side, which is important, and then on the Kubernetes side, the concept of multi-node deployments is becoming a lot simpler because the software stacks are starting to mature a bit. And so I'm hopeful that these techniques will become more and more mainstream over.
Yeah, I agree. I think that in a couple of years, probably people won't have to worry about debugging things like this. And maybe understanding the low level infrastructure is not right. Maybe it's more like be aware of it, because it does seem like it's a point that could cause latency and could cause issues. So this networking layer is still something that's people deploying or infrastructure engineers need to be aware of. I also noticed that let's talk a bit about vLLM. So vLLM has a very modular architecture. There are quite a few different repos and plugins in the vLLM organization. Why was the repo designed this way, and what advantage does that give vLLM?
So I would think about it in two ways. One is there's like various ecosystem projects. So these are projects that are related to vLLM, but aren't necessarily vLLM itself. So like examples of this are, we have a quantization library called llm compressor. We have a speculative decoding library called speculators. We have a benchmarking library called guide LLM. These are just like projects that are useful to use with vLLM, but are not the same thing as like deploying a model. So it's very natural for you to have ecosystem projects that do related things. So that's kind of one category. And there's also some plugins, which are basically out of tree hardware. So we have an overall reviewer bandwidth challenge in vLLM where I don't have access to a particular piece of hardware, and I also don't have any expertise in that piece of hardware, and I also don't have any time to review, code for a specific piece of hardware. And so a lot of the plugin system is to enable the different hardware manufacturers to be able to, have their code housed in vLLM, provide discoverability, provide an install pathway, but allow those hardware vendors who have the expertise to be able to iterate more quickly without having to be bottlenecked by, core reviewer bandwidth and lack of knowledge of how their accelerator works. And so I think that we will continuously evaluate the plugin system, and, over time, like more things may graduate to be in tree, as the project matures. But for now, where the project is in this rapidly evolving state, I think that we will continue to, kind of pursue a out of tree strategy to just make the review better. Like, it would obviously be better if everything was in tree and we just magically had 1 million people to review and like deal with these things. But the separation is really a like logistical problem associated with how we actually maintain all of the code.
I mean, by the way, the vLLM repo, the core repo, is so active.
Trust me, I'm aware. Yeah, it's pretty insane. There's over 2,500 total contributors to the project, and yeah, so it's definitely a very, very active project. So yeah, both a blessing and a curse.
Totally. There are a couple things that you mentioned that feel like they're pretty important. One is quantization, the other is speculative decoding. Can you talk a little bit about those?
So both of these focus on basically trying to optimize the model itself. So vLLM basically takes a model and runs that model as efficiently as possible. But there's also a series of performance optimizations that can be applied to the model itself to change the model in some way. So with quantization, what we're doing is converting the model from a high precision format to a low precision format. So modern GPUs have lower precision tensor cores. So tensor cores are the compute units inside of the GPUs. bfloat 16 has X flops, FP8 has 2X flops, NVFP4 has 4X the flops. So by quantizing the models to lower precision, we can increase the compute intensity and increase the number of instructions that are able to be executed every second, which can make the models run faster. And then in addition, you can reduce the amount of RAM that's needed to hold the models. So it's generally just a very useful performance optimization. And the key idea with quantization is to try to reduce the number of bits per parameter while preserving accuracy. And so llm compressor implements all the different algorithms in the ecosystem for how to do quantization while preserving, accuracy. And so lots of different model companies use llm compressor to apply different algorithms to, try to preserve accuracy as much as possible.
Okay, so llm compressor is not part of the core repo. llm compressor is also its own repo, correct?
Yeah, llm compressor is its own repo. And basically the workflow is you take a model, you apply some algorithm using llm compressor, and then you save the model in a format that we call compressed tensors. And then vLLM loads the compressed tensors models and runs them with efficient kernels. So like the models that get created by llm compressor are able to be loaded and run in vLLM efficiently. So vLLM and llm compressor like work hand in hand to deliver the end-to-end user story of take a model, apply quantization, load the model, and then run the model with efficient quantized kernels, basically. And then it's the same idea with speculative decoding, right? With speculative decoding, you train these mini drafter models. These mini drafter models predict ahead, and then the big model verifies multiple tokens in parallel. That's the key idea of speculative decoding. You have to train these speculator models. And so speculators is a library that allows you to train speculator models. And so you take a model, you train the speculator model, you save the speculator model, and then you load the speculator model in vLLM and run it efficiently. So both of those are kind of like the same key idea where you're taking a model, you're applying some ML method to it, you're getting back a more efficient version of that model, and then vLLM knows how to load and run that model with optimization. So anyways, this is kind of like the end-to-end integration between the different ecosystem projects and the runtime that we have.
How do you see the use of speculative decoding emerging? Is it getting more popular? Where is it most useful?
So quantization a while back was like a pretty unique technique, and like it wasn't really used all that much. Now it's like used all the time. And speculative decoding is where quantization was like a year and a half ago. So it's a relatively new method. It's only being used by the leading companies and like frontier users. And what's going to happen is it's going to become more mainstream. It will get easier to apply. The tools will work better. People will start releasing them all the time. The model companies will start to like include it in their model releases. And then in a year, everyone's going to be using speculative decoding, and everyone's going to be like, obviously, like we use speculative decoding. So anyways, that's where it's at right now. Is it's like used by a few people, especially the most advanced people are all using it. It's a really clean win. It has no accuracy trade-off at all. It's just like kind of a pure win. And so it will become mainstream and used more and more. But like we're not there yet. And so that's what the team is kind of focused on making happen, is like making all these techniques as easy as possible to consume.
When is it the most useful, in which use case?
It's useful for online serving. So the key thing that speculative decoding is exploiting is the fact that the decoding phase of inference is what's called memory bandwidth bound. So when you're doing the decoding phase of inference, you're doing a kind of like skinny matrix multiplication. So you have a big weight and you have a very skinny activation matrix. The activation matrix for batch size 1 with like one concurrent user will literally it'll be a vector, not even a matrix. It'll be size 1 and then the hidden dim. And so what happens is you pull the weight in and then you're only multiplying by 1. Like one of the dimensions is only 1. And so basically this is what's called memory bandwidth bound, where the matrix multiplication is bottlenecked by the data movement of the weight from main memory into the on-chip memory. And so the reason why speculative decoding works is if the verifier model predicts 4 tokens, the big model is, instead of doing a multiplication of 1 comma hidden dim, it's doing 4 comma hidden dim. And so you move the weights into the into the on-chip memory once, and you do multiply by 4 items instead of 1 item, and basically multiplying by 4 items instead of 1 item, because it's bottlenecked by the data movement, the additional on-chip operations are basically free. And so this is what's being exploited by speculative decoding, is the fact that it's memory bandwidth bound. If we can make the batch size bigger, we can basically increase the throughput without impacting the latency at all, because doing a batch size 1 gem and doing a batch size 4 gem basically take the same amount of latency. And like you can verify this pretty quickly if you do some basic timings in PyTorch. It's actually quite interesting to poke around and do this. But that's what fundamentally like speculative decoding is exploiting, is it's like turning this sequential problem into a parallel problem where you're, doing 4 tokens at a time instead of 1 token at a time. And so the best place for speculative decoding is like batch size 1 online serving, because you're in this super memory bandwidth bound regime. And so online serving, where you, in comparison to like batch throughput, where you're just like cranking the batch size as high as possible, online serving is the place where you're going to see the most benefits from speculative decoding. Now, batch inference can also benefit, especially in RL use cases, mostly because RL suffers from a straggler problem, where if you do a bunch of rollouts, you're doing the rollouts, and then, you can't move on to the next step until all of the items in the batch are finished. And so you can end up with this like straggler problem where one request is going on and on and on and on. And so if 25% of your time is dealing with these stragglers, you can have this speculative decoding problem that can help you to accelerate. Online serving is the primary place where speculative decoding gives you benefits. And the reason is this like memory bandwidth bound problem, and you're turning that into like a less memory bandwidth bound problem, and that can give you a speed up if the speculator is good enough.
Speaking of that, have you seen the Cerebras processor? It's like 900,000. Yeah, what do you think about that?
So the main thing with Cerebras and Groq, so Groq and Cerebras have similar architectures. These are what's called SRAM-based chips. I was just talking before about how in the decoding phase of inference, we're bottlenecked by the time to move the weights from the HBM memory into the on-chip. And so what Cerebras is rather than having this memory hierarchy, they have a massive pool of on-chip memory. So the reason why Cerebras and Groq are so good at this decoding phase of inference is because they're not bottlenecked by data movement from HBM into on-chip memory. They just have a ton of this like SRAM memory. And I don't know too much about Groq's architecture, but Cerebras has like a very interesting like manufacturing process and things that they do to make that work well in a single large wafer. And so Cerebras and Groq are very interesting chips because they're making like a totally fundamentally different design trade-off relative to standard GPUs that makes them really, really good at this decoding phase of inference. And so I think what we will see over time is the accelerators becoming heterogeneous in this way. So you've seen this from NVIDIA, where on their Vera Rubin systems, they're going to have this Groq LPU, which will be used specifically to process the decoding phase of inference. And then they'll use the regular GPUs for doing prefills and for doing the attention operation in inference. So they're going to do attention, feed forward, disaggregation. You can look at the chart from GTC, but like the Groq chips will become this specialized accelerator for the decoding phase of inference. And then Cerebras has announced a partnership with AWS where they're going to use the Trainium chips for prefill and the Cerebras chips for the decode phase of inference. And so I think that, Cerebras especially will play a key role, especially for folks that are focused on super low latency inference. And then I think they have an opportunity to inject themselves into broader systems where prefill is going to run on chips that are optimized for doing batch, such as Trainium or a GPU. And then they'll specialize in the decoding phase of inference. And this could be a really, really big boom for them. So the disaggregation of serving provides lots of opportunities for specialized chips to come in and deal with the different phases of inference and make much different design trade-offs. So that's my overall take on Cerebras. They're great to work with. I've worked with Cerebras for a while. Even when we were at Neuromagic, we worked with them on some like sparsity projects. And so they're, they've done really, really well. And they only pivoted to inference in relatively recent time. And that's driven like a huge boom in their business. So yeah, I'm definitely cheering for them to do well.
Yeah, it's definitely interesting technology, especially how they built it and how they overcame all the hurdles, how the plate cools, how the wires are on the processor. It's just really interesting technology. You mentioned reinforcement learning. Does vLLM also support reinforcement learning?
Yeah, so one of the major trends that's been happening in the ecosystem is really since like O1 from OpenAI, which was the first like reasoning model. The way that these reasoning capabilities have been injected into the model is through the GRPO algorithm, which is a reinforcement learning algorithm. And this has driven a huge amount of improvement in the model quality and is arguably the thing that's currently being scaled by all the major labs to drive recent breakthroughs. Obviously, people are continuing to innovate in pre-training, but RL is where there's like a lot of energy in terms of like adding new capabilities to the models. And so RL systems have three parts. There's an inference system, which basically rolls out a bunch of different potential responses in parallel. There's an environment, which evaluates the responses that the model creates. And then there's a training system, which backpropagates the loss based on the verifiers, the environment's scoring of the different rollouts that the inference system had. And it turns out that the inference component of the system is a very, very significant amount of the compute cost to run an RL system. So inference engines are very fundamentally important performance optimizations for these overarching RL systems. And so systems like vLLM and SGLang are heavily used across the industry for doing rollouts, in RL, in both from large labs as well as from like open source projects like PrimeRL, for instance.
Also, another consideration is mixture of experts and parallelism. Can you talk to me a bit about these features or how they're supported?
The other key thing is the model architectures have shifted towards these mixture of experts models over the course of the past few years. So starting at the beginning of 2025 with DeepSeek, pretty much every new model that's come out since then has had this mixture of experts architecture, especially for anything of scale. And so the mixture of experts architectures have a couple of different advantages. For online serving, they're useful because you're only going to activate a small percentage of the experts per forward pass. And so there's just much less compute that's needed to run the forward path of the model, which can help with latency. But then in addition to this, these models can also scale well to multiple nodes because we have a different parallelism scheme that we can use. So for standard dense transformers, you have this Megatron sharding where you're going to do tensor parallelism and shard each individual weight, split that weight into different GPUs. And then there's 2 all reduces per layer to basically synchronize. And this is very bandwidth intensive. All reduce is very bandwidth intensive. So you really don't want to do them except over NVLink. You don't want to do them over multiple nodes. And so one of the things that Mixture of Experts enables is you can have a different parallelism scheme where you do data parallel attention, expert parallel for the MOEs, and then we can use different collectives, basically these sparse all-to-alls called dispatch and combine. DeepSeek's open source week, they released DBP and DeepGem, which are basically the compute and collective kernels that are needed to do these operations. With this parallelism scheme, you can scale the models to multiple nodes. This is really, really useful in batch and RL use cases where you want to increase the batch size as large as possible, and having one copy of the weights spread over multiple nodes over 32 GPUs or over 72 GPUs or over 128 GPUs, it allows you to use all the additional RAM for KV cache space, which allows you to crank your batch size up, which allows you to get as much throughput as possible out of the models. So in general, the Mixture of Experts architectures are much more efficient, both for training and for inference, and they create a lot of opportunities to do these types of performance optimizations, especially in the RL context. So we've worked with a lot of RL users to set up these basically deployment setups.
Can you maybe back up just a little and talk about why Mixture of Experts can have this different architecture?
Well, the reason is basically in the in the MLP layer, there's basically the following operations. Each token goes through a router, and then that token, the router, which is part of the model, the router is learned, for each token predicts which experts should be used. So let's say we have 256 experts, and each token is going to get routed to 8 of the 256 experts. That's what DeepSeek has. The router says, okay, for token 2, it's going to be routed to expert A, B, C, D, E, G, and F. And then what this allows is, since you're doing sparse, which means you're not sending it to every expert, you're only sending it to the top K, the top N, the top 8 experts. Then after the routing, we can use those top K IDs to send the tokens only to the ranks that they're going to be processed on. And so because the models are very sparse, meaning only 8 of 256 experts get activated per token, we actually don't have to send that much data around, basically. And so this means that this dispatch operation consumes not very much bandwidth, which allows it to operate over these slower networks like InfiniBand or Rocky as compared to these faster networks like NVLink. So anyways, that's the overall intuition, is the sparsity of the model gives us a different dimension that we can shard on, and we can exploit that sparsity to do basically sparse collectives that don't need that much bandwidth, which therefore scale better to these multi-node environments.
Do the experts ever get hot? What if you're always routing to the same 8 experts? Does that
So certain experts, so it depends on your traffic pattern. Experts won't get hot. It's deterministic routing for each token, but different traffic can activate different experts, right? It depends on what the router learns which token should be sent where. And so depending on your traffic pattern, you can start to see certain experts becoming more utilized than other experts. So we actually have something called EPLB, which is expert parallel load balancing, which allows you to have multiple copies of certain experts. And then while vLLM is running, it's keeping track of how much, it has a rolling window of which experts are hot. And then every n steps, it reshuffles the experts to replicate the most popular ones to try to balance things as much as possible. So this is actually a quite important performance optimization, especially for the prefill case. There is algorithmic techniques. It costs additional memories. Let's say you have 256 experts, you're doing EP32, you're probably going to want to have 32 additional expert slots. So it consumes more memory, which obviously has a performance impact, but in general, it's a useful optimization, and most people apply it to RL use cases.
Well, most larger models are using this Mixture of Expert model architecture.
What's happening is that any model of any size these days is mixture of experts. Dense models are still released, but like the biggest ones that you'll ever see these days are like 20, 30 billion parameters at most. And above that size, everything's mixture of experts. And because it's way more efficient to train and way more efficient to serve. So it's just a way better architecture. Everyone is like using it now. Basically, since DeepSeek came out, everyone has shifted to doing this. And I suspect that the OpenAI and Anthropic have been using these models for a long time.
How does different parallelism come into play? There's expert parallelism, tensor parallelism. How does this come into play with these models?
Yeah. So the different parallelism schemes are useful for different deployment patterns. So I talked about DPEP, for instance, for these like batch-oriented workloads. That's going to be really useful for a use case that's trying to maximize throughput at the expense of latency, or is trying to maximize KV cache size for long context serving. Whereas if you're doing absolute latency minimization setup, you're probably not going to want to deploy a PD-disag DPEP setup because it's not latency minimizing. So basically different deployment patterns, depending on what you're trying to optimize for, could potentially use tensor parallelism and, a throughput maximizing workload where for batch or for RL might want to use this DPEP kind of setup. So I talked before about like why an operator needs to understand the internals of vLLM. This is an example of like the type of knob that someone should be tuning is, am I doing a batch throughput oriented workload? Okay, therefore I need to maximize my KV cache shape, therefore DPEP, versus like someone who's thinking, okay, I'm trying to get the minimum possible latency. I want to run at tensor parallelism. I want to run at batch size 1. Okay, I should use tensor parallelism, basically. So it's something that is use case driven in terms of which parallelism scheme you might want to select for the current deployment pattern that you're thinking about.
So this leads into a discussion around flow control and scheduling. What does this flow control feature give you?
Yeah. So flow control is an llm-d feature. So we talked a little bit before about some of the request scheduling features that llm-d has, where it's doing like prefix cache aware routing or load aware routing, where it's selecting the optimal pod for each individual request. There's another dimension, which is called flow control, which is intelligent request queuing. So if prefix cache aware routing, load aware routing is about intelligent request scheduling, flow control is about intelligent request queuing. So when is queuing useful? Queuing is useful when the servers are oversaturated. And there's really two use cases for it. The first is if you're running a multi-tenant deployment, where maybe you have workload A, workload B, workload C. All of these workloads need to consume GPT OSS. Very commonly, people will start by deploying 3 different endpoints for 3 different tenants. And maybe tenant A is a really important customer-facing application, and tenant B is your ML developer who, is not that important. No offense, but they're not running a production, they're not running a client-facing application. So because these different tenants have different levels of priority, platform teams will often separate those into separate deployments so that you don't have a noisy neighbor problem where, the ML developer runs a batch job and now all of a sudden you can't process any inference requests for your critical service, right? And so one feature that queuing enables is when the servers get oversaturated, how do you prioritize amongst the requests? One thing you can do is set some type of traffic to be premium, some type of traffic to be standard, some type of traffic to be best effort. And when the system gets overloaded, prioritize the most critical requests over the less critical requests. And this can allow you to consolidate multiple different applications onto the same set of resources, which is really important. And I'm fired up about this feature because I've seen a bunch of users having this exact problem. And so I'm hopeful that we can get some of these folks into production with this flow control feature soon. The other thing is for single workload, where single tenant use cases, especially for batch oriented use cases, delaying when we dispatch the requests is useful because we can prevent the bad decisions. So if we had 20 requests and 4 servers, and each server is processing 5 requests, if server A somehow gets lucky and finishes all the requests quickly because it only had short requests, then but we already dispatched all the requests into pod C. We can't move the request to pod C. So the other thing that flow control does is it allows us to have this spot where we can do late binding of these requests and do the queuing in the router layer as opposed to the vLLM layer, which can allow us to basically make a more informed decision later in the request lifecycle about which pod should process the request. So those are the two use cases. It's async processing, batch-oriented workload smoothing thing, which I think is useful. And then this multi-tenant situation where you want to do fairness and prioritization. These are like the key reasons for flow control.
That sounds really useful. What are you using as the queue?
So for the batch-oriented workflows, like there's a couple of things. One is in the llm-d upstream project, there's a few different integrations like GCP PubSub or like Redis where, you can write to a queue. And then we also have this thing called like the batch gateway, which implements the OpenAI protocol for doing batch workloads. So the user uploads a file and then the batch workload like dispatches all of these components that do this work in the background. And then you get back a file a few hours later. So I think both modes will be useful. Maybe some more like advanced users might want to customize the job submission process and we can compose with that. And then for I think a lot of other users who just kind of like want this API, they should be able to kind of have that platform level stuff they don't have to know the details of what async processor is happening. They just call the batch gateway. And
Yeah, I see. So what happens when the traffic becomes a bit unpredictable? Like let's say it's bursty. How would the flow control handle that if it had just dispatched a bunch of batch workloads, for example?
Yeah. So like in the current setup, the flow control feature will not dispatch requests beyond. One of the things you can do is have a concurrency control. So don't let any of the pods get more than 32 requests in the system at a given time. And like if the batch request comes in, like it's going to start queuing requests as soon as we hit the 32 threshold. And then let's say new requests came in that were part of the premium traffic. Those would move immediately to the front of the queue ahead of any of the additional batch requests, and those will start getting processed. So that's the current as is state, which is you have these concurrency based targets. These are, once the pods hit those, we stop dispatching requests, start queuing, and then in the EPP, that's where the new requests will move to the front of the queue if they have more important priority than, the batch request. And then what we're working on now is actually like eviction. So the EPP detects that the pods are saturated and a new request comes in that's higher priority than the batch request that's running in pod A. We actually want to evict that request from pod A and then dispatch the new online request immediately. And so that would be eviction based, where currently once the requests are dispatched to the pods, they're committed and the pods eventually it will get unsaturated and then like we can start doing the new requests. But while the pods are saturated, like there's nothing, it's saturated. But this eviction based mechanism will allow the system to react more quickly to the case where this high priority traffic like comes in. And so I'm pretty excited about that. That will be part of like the 0.8 llm-d upstream release, this eviction mechanism. So Rishab is working on this right now.
And when you evict the processing of a request, you have to start all the way over again, right? In this scenario, like whatever progress you have made, you won't use it the next time, right?
I mean, I think you could think of like different implementations. Like one implementation that you could have is to stream the response and then start gathering it, or when it gets evicted, like you somehow like get the partial progress and then retry it. So I think there's like probably implementation details that you could have to like capture the intermediate state. I think the first implementation will probably just be retries for those things. And I think we'll basically have different levels of priority. So there's numeric scores for the priorities. And like, if it has a negative priority, we could potentially call this sheddable, and it will immediately kill those requests, or those will be evictable. And then things that are higher priority maybe like won't be evictable. And so that's, I think, how we would probably implement it.
This seems very useful because it increases the GPU utilization. So this seems like this will be really useful for people.
I totally agree. I think that this stuff can be quite impactful. I think the piece it's definitely a little bit of a more complicated setup than like prefix cache-aware routing. Prefix cache-aware routing is just such a clear improvement over a service, and this flow control stuff is a little bit of a different concept. So I'm not sure it's going to be like as broadly applicable as the routing stuff, but I think for the customers that understand the value of it, they really get it. They really like it. We kind of have had this feature in experimental mode in the upstream project, and now we're really going around and trying to get some users of it. And so I'm very curious for it to get like rolled out into production and start getting some success stories and whatnot, because like I do think it can drive like quite a bit of consolidation of different bespoke endpoints into these multi-tenant shared endpoints, which I think will really, really, really help to improve GPU utilization.
So llm-d has an endpoint picker that helps to route to an instance of a model. What other routing and scheduling features are important or are you excited about in llm-d?
Yeah, so the EPP is like where the brains are. So this does the request scheduling. The features I was just talking about for flow control are implemented there. So the EPP is really like the guts of vLLM. That's where most of like the smart logic is. In front of that is where some additional orchestration things sit. So, things like the batch gateway or the async processor, which can be used by the batch gateway to do these batch requests, are different components. So those are the things related to routing. I don't think there's going to be more like routing stuff besides those. But then
I think I saw there's like SLO aware routing, right?
So the latency aware routing is part of the EPP. So there's like a sidecar that gets deployed with the EPP that does predicted latency based scheduling. So these are just, I don't think of that conceptually as different. The EPP by default does a linear combination of the different signals to predict which pod. The latency predictor trains an online XGBoost model based on the things to select which pod. So it's an enhancement over the baseline scheduling that we have, but it's still kind of part of the EPP. So we have the async processor, batch gateway, EPP. Those are the router level. That's like actually dispatching requests into vLLM. Then we have some workload APIs. So we work very closely with the leader worker set community. Leader worker set is what's doing the multi-node orchestration. So this is what schedules the pods over multiple nodes. We're collaborating with the queue community for topology-aware scheduling. And then Mistral actually open sourced an operator called the disaggregated set operator, which is based on leader worker set for doing rollouts of PD disaggregated deployments. So we have these workload APIs, which are all underneath llm-d, but we work very closely with those communities to integrate them. And then we have some auto-scaling APIs. So we have this thing called the workload variant autoscaler, which I think is quite useful. And the workload variant autoscaler, is another component that handles the autoscaling part of llm-d. So those are like the major pieces. It's like the router level stuff, which is the EPP, and then some higher level orchestrators on top of that. There's the workload APIs with leader worker set, queue, and disaggregated set. And then there's the workload variant autoscaler piece. And those are like the major components of the project.
So you're obviously deeply technical, but you're also very customer facing. Why do you think that combination right now is so valuable?
In general, I think that customer centricity is useful regardless of the industry that you're working in, because at the end of the day, the hardest part is figuring out what to build and is identifying the customer problem that you're trying to solve and having like as close of a cycle between that and engineering and product strategy is just generally useful for any sort of new business that gets created. I mean, I think it's especially acute in AI because the market is evolving very quickly and things are changing very quickly. But I think customers to product very quickly is just a very useful mindset, regardless of AI or not.
So you get pulled in a lot of different directions. Like, obviously, you're very busy as well. How do you decide how to prioritize your time and which interactions will create the most leverage for the company?
I generally like to, on a monthly basis, look back at what I accomplished and where I was focused and try to be honest with myself about what's working, what's not working, and not get too high or too low about like what's been happening. And so I generally use that kind of monthly cadence to like set my priorities of what I'm going to focus on and what I want to accomplish. So I try to go from that OKR based approach of I'm trying to get this objective or this outcome. What do I have to do to like make that happen? And then I like to try to work on it myself, but I also like to try to rally people around the cause and like evangelize, the outcome that I'm trying to make happen. So I think that's like another thing is I like to be very collaborative. If I'm seeing this thing happening in a customer, like I want to tell as many people as possible about it and get them excited about it. And that can create momentum around the different initiatives that I'm working on. So that's probably what I would say is like I try to be pretty like explicit about, for instance, this year I'm focused on success of the communities that I work in, vLLM and llm-d, from a holistic perspective, project operations, project health, marketing, make those projects successful, and customers. And then anything else I don't do. So it's that's I think like a key thing is being very focused on the outcomes you're trying to drive and then evangelizing it and trying to get as many people as excited about like your mission as possible are the things that I guess I've stumbled upon to get those things done.
What lessons have you learned from talking to customers and interacting with them?
One of the things is empathy, which is the customers have a lot of things going on. They have a lot of competing priorities. Whatever issue that they're running into is usually a critical thing if I'm getting involved with it. And so, that's like one thing is really listening and understanding why you're falling short. So that's one. And then the other thing is just being in the trenches is great. If they have an issue, like you really want to care about it. You want to respond very quickly. You want to work very closely. So that's another kind of key thing. And then the last piece is it's very easy to like get caught up in technical jargon, especially when we're working on pretty complicated technologies and interesting technologies. So the other thing that's important is to try to tune the level of the conversation to what the customer knows. And so, if we're going to spend talking about vLLM to someone who understands LLMs, but like isn't an ML engineer, if you start talking in too much detail about the intricacies of how the KV cache mechanism works, then they're just going to be lost. So the other thing that's useful is to just be able to effectively communicate about the different layers of the stack and understand what the person you're talking to knows, what they need to know, and dialing the level of what you're communicating up or down to what is going to actually help them versus what's going to make you sound smart is generally like a useful strategy. And then the last thing I would say is I'm very enthusiastic and I bring a lot of passion and energy to what I'm doing. And I think that is a useful way to get folks like excited about what you're doing and make them want a part of what you're building. So yeah, those are some things.
The energy is good. Definitely tuning your talk to your audience is very important too. Okay, so I have a couple of rapid fire questions. One is, how do you use AI in your daily life? Like not professionally.
I mean, I pretty much use, these models like on a day-to-day basis. Really, anything I'm trying to do that's written, they help me with. Medical, trying to write a thank you note, like really anything these days. But they're really, really good at debugging distributed errors. So that's my primary use case.
Honestly, true. So true. So what do you think is the most underrated optimization in AI inference right now?
Definitely a prefix cache reuse is like more profound than I think people even really understand. So all these different things are effectively trying to make the KV cache as big as possible and reuse it as much as possible. And so every single thing we've talked about is basically built on that fundamental concept.
If you could instantly fix one bottleneck across the entire inference ecosystem, what would it be?
I would say like probably the biggest paper cut is all the, tool calling stuff is totally messed up and it ruins people's user experience, especially with the local models. So I think if I could snap my fingers and like have all the bugs fixed from those, and there's a total like long tail problem, which is all the model companies like create their own parsers and like they're always super buggy and they don't really work that well. And so we've had a huge initiative to clean all this stuff up. And I know this is just going to be something that like we're working on for like years and years and years to fix all this stuff. So that's definitely one thing I would like clean. I would just, if I could snap my fingers and like have the problem go away, I think it would probably be that.
Yeah, lack of standardization is definitely a paper cut. What is one thing every infra engineer should understand about AI?
I would go back to that prefix cache reuse and sizing thing. That's like fundamentally all the different parallelism schemes, all the offloading stuff, all the prefix cache awareness, all those things just come down to prefix cache reuse. And so having like a KV cache centric both operator mindset and then thinking about that through all the different layers of optimization, that's where, if you're running AI, having that mindset when you're observing, operating, and optimizing the system is what I would focus on if I could give one piece of advice.
What is one prediction in AI that you're confident in?
The models will keep getting better.
That's great. What is something that customers consistently ask for that surprised you?
One of the main things is this semantic routing between cloud models and on-prem models. I was pretty surprised by that, but that's been popping up in like every single meeting I've had. So we need to get cracking on like getting it into our production quality systems.
Is it surprising because you didn't think that they would be so hybrid?
That's part of it. And then I think the other piece is I thought maybe they would want the application developers to have more control. Like the application developers would demand more control over what model they were using versus like this shifts the model decision to the infrastructure provider. So that's mostly like what it kind of is it shifts the kind of like decision of which model away from the application developer towards the infrastructure provider. And I actually am somewhat surprised that, I mean, I also talk a lot to infrastructure providers, so maybe the application developers will have a different perspective about that. But the main reason why I find it surprising is I thought that the application developers would demand more control over exactly what model is used in which case. And also I have had situations where it's a total opposite, where it's like I'm getting scrutinized about like log probs being 0.001 different than something else. So anyways, I just have some cognitive dissonance about different places that I've worked with platform teams in terms of what the end users are demanding for consistency between subsequent queries.
Yeah, I think cost definitely plays a role in there too. So that's all I have. Do you have any last words or a piece of advice for our listeners?
No, I mean, thank you so much. We covered a lot of ground, and hopefully people enjoy the discussion. llm serving is a super interesting field, so if you're interested in working on these problems, we're hiring in Red Hat, so please apply.
Yeah, thank you. Thank you so much for listening to Alexa's Input AI. And if you want to follow along with my new episodes, writing, content, everything I'm building, you can find me at alexagriffith.com, on Substack, on YouTube, or wherever you listen to podcasts. If you enjoyed this conversation, it would mean a lot if you subscribed, shared this episode with a friend, left a quick rating or a comment to help more people to discover the show and keep these conversations going. Again, I'm really grateful you're here. This podcast started as a side project for me a few years ago, and every listener who reaches out or keeps coming back reminds me exactly why I love doing this and I love putting so much time into it. I hope this episode gave you something to think about, something to talk about. So always stay curious, stay grounded, and I hope to see you next time. Thank you for your support.